All right, so we continue with chapter 12. So the next is going to be rotational dynamics from the point of view is that, why the object is rotating. So let's say if you have a disk or if you have a sphere or something like that, right? What do we need to do to make it rotate? Well, to answer that, we're going to look at in terms of the requirements, right? To be able to successfully rotate the system, and our ability to rotate the system successfully is known as a torque. Then this torque is to rotational motion as force is to the linear motion. Remember, right? In order to make the object, you know, start moving from rest, we needed to give it a push. Well, same thing here is for us to make the system rotate, we need to apply torque. Okay. And the question here is that, okay, so what is a torque, and, what are the conditions, what are the requirements for us to apply torque to a system so it can rotate? Because it's not quite as the same as just applying force, because torque has to rotate the system. And so far we have seen, right? So let's say moment of inertia is not quite the same as the mass, so then the torque is also not quite the same as the force. So let's look at here in terms of, you have a wrench and you're trying to rotate um, some kind of a system here, and our ability to effectively make rotate the system will be depending on number of things. First, obviously there has to be a force acting on it. So um, and the force that has to be acting also, you know has to have right conditions. So for example, if you're applying a force, see, if I apply force right here, well, this force is not successful. It's not going to be effective at rotating the system. If I apply force like this, it's also not going to be effective. If I apply force like that, it's also not going to be effective. That means there has to be some kind of effective way of making this rotate. So two things we need to have here is there has to be a force. That's obviously given, right? To make it rotate, there has to be a force. But there also, with respect to the pivot point, which is basically our axis of rotation, this force has to have some distance r from this axis of rotation, basically non-zero distance. So you can see, right? If I apply here, it is exactly at the pivot point, so that is not effective. So there has to be some kind of, this distance r that is, let's say, non-zero. Okay, and the force, let's say, non-zero force. So there has to be force, non-zero distance, but also such that I'm going to use this angle phi. So angle phi, that is the vector, or you can say angle between two vectors. Well, force as a vector and technically r as a vector. This r as a vector. So think like this. If I have this as a vector like that, then phi here is the angle measured counterclockwise from the radial line. So you take that radial line and you measure that. So then phi here, basically you can say that cannot be zero, or also cannot be 180 degrees. Because if it's zero, the force is, let's say, acting in this direction. It's not going to rotate the system, right? The wrench. Or if it's in this direction, again, it's not going to rotate the wrench. That means effectiveness of a force at causing rotation is called torque, and torque is a rotational equivalent of the force. Okay, so, and these are now some of the requirements for the torque to be effective. That means there has to be a force. Force has to be acting at some distance f, some distance r, such that r is basically non-zero. And also, when the force, you look at the orientation of the force relative to that radial line, it's not along that radial line, basically. Okay, so then if you plug in everything together, we have then this Greek tau is for the torque. So then torque depends on non-zero position, non-zero force, and sine of phi. So that's why you can see, right? Phi, when is 0 or 180, sine of phi goes to 0. So the torque is 0. So that's why what we have here is the torque, which is our ability to rotate, right? Effectiveness of the force to rotate the system is equals to R times F times sine of phi. That means R is a distance in meters, F is, in newtons. Then sine of phi is basically unitless. So in a way, the units are meters times newtons or newtons times meters. So that's the units for the torque. Okay. So newtons times meters or meters times newton doesn't really matter. So, and then what we have here is the rotational direction, counterclockwise and clockwise, can also be used to give us direction for the torque, because torque is a vector. That means it has a direction. So whenever the torque basically give us a rotation that is counterclockwise, then it is positive. Whenever the torque basically gives us a rotation that is clockwise, then it's negative. Okay. Again, let's summarize it. The ability of a force to cause rotation depends on the magnitude of the force, the distance r from the point of application to the pivot, and the angle at which the force is applied. So that's why what we can see here is, you know, our ability to rotate is much more complicated than our ability to push something, right? So that's why in a linear systems, things are a little bit more simpler. In a rotational, it's more complicated. Not only force, but how far away the force is from the pivot and what its orientation is. Okay, so here's, you can see that, for example, you have, you know, I don't know, let's call this 1, 2, 3, 4, 5, and 6. So you have 6 different forces acting on this wrench, and you want to know in terms of the torque. So let's say torque 1. Well, torque 1 will be then, if I'm looking at this, right? So here's the distance r. So it will be r times f1. Since all of them have the same exact distance r, so r times f1. And since it's perpendicular, so the sine of phi is 1, so the r times f1. That's torque 1. Let's look at torque 2. Well, is then r times f2, and then you basically look at this angle phi, then sine of phi. All right, so that means this is actually less effective because you're going to get a smaller number. Let's look at torque 3. Well, torque 3 is r times f3, then sine of, well, here's a force, which is, you know, here's a here's the force. In this case, the phi is basically 0 because the force is along the same line as, you know, vector r, right, on the radial line. So this guy here is 0. Let's look at torque. By the way, also you can see, right, 1 gives us a, you know, sensation of like rotating this counterclockwise. 2 is also rotation counterclockwise. So this is positive, and this is positive. Torque 3 is 0. Torque 4 then will be r times f4, then times sine of phi, and then, you know, basically you can see, right, so if you do this, then your sine of phi itself already going to give you a negative. So it is basically a negative torque, because also its sensation going to be like, let's say, rotating its counterclockwise, clockwise. Oh, here counterclockwise, sorry. And the same thing with 5, right? Counterclockwise rotation. So torque 5 is equals to r times f5, then sine of 270, right? So there's going to be then 270. Or you can just basically do this as I say, if it's 90, but then manually put the negative sign. And obviously, finally, torque 6, which is then rf6, then sine of, and then you can see, right, it's 180. So that gives you 0 again. So this is not effective. This one is not effective. And you have then 2 positive ones and then 2 negative ones. Okay, so that's, you know, kind of similar to when you're being pushed to the right, positive, to the left, negative, right? All of those things. So because one of the things we can do, we can also solve for the net torque, which is the sum of all the torques, just like we would have done with the net force, adding all the forces together. All right, so one other way, which is, you know, sometimes simpler, sometimes not so much, right, is to find a torque using the moment arm or the lever arm. So this one is taking the force and drawing, let's say, the line of action. Here's a line of action of the torque, or the force. And then the distance from the pivot point directly perpendicular to the force. And then basically torque is equal to just d times f, rather than this r times f sine phi, right? It's just d times f, which is in a way, you know, you're going to get exactly the same thing. But sometimes actually, I will show you in some cases, right, it ends up being a little bit more, a little bit simpler when you're using this, let's say line of action and moment of arc. So in this particular case, one thing you can see here is this. See, this line of action for a force can also tell you if the torque is effective or not. See, for example, if I have a force like this, see the line of action of this force goes through the pivot point, so it's not effective. If I have a force like this, its line of action goes through the pivot point, it's not effective. That means if line of action of any force goes to the pivot point, that force does not give you torque. Okay. Now, what is the sign of this torque over there? Think about it for a minute. And I'm hoping you guys can say that it's positive, right? Because it's going to give you counterclockwise rotation. So the sign of this torque is positive. All right. So sometimes you can have an object that has more than one force acting on it and it's successfully rotating. That means, or you can say more, let's say several, torques exerted on the system. So then we can say, all right, so there's F1, F2, F3, F4, and F axle. So then to find the net torque, we have to just add them all together. The one that's going to give you, so let's say here's you have like, let's say, so this is R1, and this is R2, this is R3, this is R4, and then you can from here see the sensation of the clockwise to counterclockwise, and obviously you can do like a line of action. See the line of action of this one goes through the axis of rotation. This one not, this one not, this one not, but the axle does. That means F1 is not effective, F axle is not effective. All the other ones can actually be then giving you a contribution to the net torque. Right, so I have a simple example where we can see that. So you have a thin disc-shaped, two thin disc-shaped wheels of radius RA equals 30 centimeters and RB equals 50 centimeters are attached to each other on the axle that passes through the center of each, as shown. Calculate the net torque on this compound wheel due to the two forces shown, each magnitude of 50 newtons. All right, so then I can say, right, net torque is equals to, remember they're vectors, right? It's sum of torque A plus torque B, just like, you're doing net force. So then I can say, all right, net torque then is equals to, I can see that this is the distance for the force A and this is the distance for force B. Also that, force A gonna give me counterclockwise rotation, so it's positive. Force B gonna give me clockwise, so it's negative. So it's basically torque A minus torque B. Torque A is RA, then times FA, then times sine of angle. I can see it's 90 degrees. Then minus RB, FB, then sine of, and I can see from here, let's say sine is then, this is 60 degree, right, with respect to the radial. So sine of 60, but I already included, let's say, I could have just done this, but it's same thing, right? You do sine of 60 and then, put the negative manually. So then I can do this and then calculate, after plugging in the values, right? So basically point 0.3 meters, because you have to convert to meters, right? Then times 50, times 50 newtons minus then um, 0.5 meters. Right, I don't know what's going on here. All right, so 0.5 meters, then times 50 newtons, then sine of 60. And if we calculate this, we're going to get negative 6.7 newtons times meters, which means the net torque is negative. That means this disc will start rotating clockwise. Because the net torque is negative, means then the rotation going to be in that direction. All right, so another thing we have is that the torque due to gravity is found by treating the object as if all the mass is concentrated at the center of mass. And this is something that we can always assume that any object can be thought of as where all the mass is concentrated exactly at the center of mass. So then you can see, right, Then here's the center of mass. So then the mass, since it's concentrated at that point, then gravity only acting at that point. So then the gravity is a force, which is equals to total mass times g, right? mg, acting on it to make it rotate. And if this is the axis of rotation, it's going to start rotating with respect to that axle like this. And gravity, torque due to the gravity is mg times x. Mg its magnitude, x center of mass is distance, and negative because it's a clockwise rotation. All right, so let's look at an example here. We have a 4-meter long, 500 kilogram steel beam extends horizontally from the pivot, from the point where it has been bolted to the framework of a new building under construction. A 70 kilogram construction worker stands at the far end of the beam. What is the magnitude of the torque about the point where the beam is bolted into place? All right, so I have a picture over here where you guys can see. So one of the things is important here is to identify your object of interest. Well, here object of interest is the beam, right? Because it says what is the magnitude of the torque about the point where the beam is bolted into place. That means force acting on the beam, so you can find it. All right, so that means you have this beam as your object of interest, and you have then 3 forces acting on it. One is the normal force, right here, right? Uh, the other one here is because the beam has a mass of 50 kilogram, then you can assume that all the mass is concentrated at the center if it's uniformly distributed. Remember, its center of mass is exactly at the center, like I showed you in an example, right? Where if it's a rod, center of mass exactly at the center, then the gravity acting over there. So if it's a 4-meter long, then with respect to this, left side, which is the origin, gravity acting exactly 2 meters to the right of that. Then we have a worker standing. So this worker then, exerting force equals to its weight, which is then 70 kilogram acting exactly 4 meters, from this. We're going to take this to be our pivot point, right? With respect to our pivot point. And what we want to know is that what is the magnitude of the torque about the point where the beam is bolted. That means what the net torque taking that point O to be the axis of rotation. All right, so the next net torque is equal to the torque due to normal force plus torque due to the gravity plus then torque due to the, I don't know, let me put like as a weight of the person, let's say. Okay, and this is the weight of the beam. Like that. All right, so one thing I can see here is this. Remember the line of action? So if I do line of action for normal force, see it goes through the axis of rotation to my pivot point. That means it doesn't do any contribution. So then I can say that this is 0. Then my net torque is equals to, so then I look at in terms of the torque due to weight of the beam. So it will going to be R of beam, then weight of the beam, let's say, right? And then times sine of the angle, right? So sine of, I can put this as negative 90, or I can, do it like this, right? Or I can just put 90 and manually put the negative because you can see, right? It gives you counter clockwise, and this one also gives you clockwise. And then plus our person times the weight of the person times again sine of negative 90. Okay, so this becomes, let's say, 2 meters, then times, so what is weight? So the beam is 500 kilogram, then times 9.8, right? Then times sine of negative 90, then plus 4 meters for position of the person. Its mass is 70 kilograms, so 70 times 9.8 is weight, because it has to be weight, not the mass. Then times sine of negative 90. All right, so what we do here is we calculate, we're going to get negative 12.5 kilonewtons times meters. So that's basically the answer. Okay. Now, in order for this person to be able to successfully stay there without, this entire thing is rotating, that means in a way, the normal force over there has to give us enough, let's say force, right, to keep everything, to be at rest, or like, let's say. But otherwise, in terms of the rotation, this means that this thing will be rotating counterclockwise. Right? So this thing will be rotating counterclockwise. All right. So we talked about rotational kinematics. We then talked about what causes the object to basically, rotate. Then next we're going to be then connecting, which basically is rotational dynamics, right? That's now we're going to be connecting kinematics with dynamics. Similar way when we said that net force is equals to mass times acceleration, and acceleration can be used with those kinematic equations. That means, what is the link between kinematics and dynamics? Well, the same thing is here. So when there is a net torque acting on the object, what does it make object do? What does it do to the object? Well, it makes the object to have a angular acceleration. That means the net torque causes an object to have an angular acceleration, similar to as the net force causes object to have a linear acceleration. Even the equation has a similar format. Net net force equals mass times acceleration. Net torque equals mass equivalent, which is moment of inertia, then times angular acceleration. So this is the rotational second law for the rotation, or you can write it like this in terms of the angular acceleration. So alpha equals net torque divided by moment of inertia. All right. So that means if there's a non-zero net torque acting on an object with moment of inertia I, there's going to be angular acceleration. Angular acceleration means the object is going to start speeding up, slowing down, or spinning faster, spinning slower, and things like that. In the absence of net torque, when a net torque is zero, the object is either doesn't rotate, which is in static equilibrium, or rotate with constant angular velocity, which is dynamic equilibrium. That means you can have a disk which is rotating at constant speed, constant angular speed, right? It doesn't speed up or slow down, but it is, moving at some constant rate. But as long as there is no torque, the speed will not change. If it's zero, it's going to remain zero. If it's 5 radians per second, let's say it's going to remain 5 radians per second. In order for there to be change in angular velocity, there has to be a net torque, which gives us the angular acceleration. So, kind of summarize, we have then rotational dynamics and linear dynamics and kind of equivalent of those, right? So you can see that net torque equivalent to the net force. Mass equivalent is the moment of inertia. Acceleration equivalent is angular acceleration. And this is the second law for the linear system. This is the second law for the rotational system. Alpha equals net torque over I. Okay, just like A equals net force over mass. So this is kind of like, let's say, problem solving, let's say strategy, right? So model the object as a simple shape, draw, a picture, try to do the free body diagrams and things like that. It's been kind of disappointing to see how many of you are not using the free body diagrams, which are very, very useful, very, very important. So try to use the free body diagrams. They're very important, and they always help you to visually see what's going on. And basically you have to kind of figure out, right? So in terms of is the system is rotational kinematics or rotational dynamics, is it in static equilibrium or dynamic equilibrium, or it is rotating with some angular acceleration and things like that. So but always having the coordinate system, having the free body diagram, which allows you also to look at the torque and also the orientation of the torque, right? Clockwise, counterclockwise, and things like that. Then you can basically combine them all together in this equation along with the kinematic equations, right? So and solve the problem. Okay. Now, one thing we're going to be start doing here is, if you remember in previous chapters like 6 and 7, when we were talking about, let's say, two objects connected by a string that goes over the pulley. So one thing we always said was that pulley has no mass, has no friction, and also the string, basically has no mass, and so the tension on both sides is exactly the same. Well, we're going to start changing this a little bit here in this chapter, because think like this. If let's say you have a disk like this, and disk has basically two forces, one force, let's say tension 1 here, another one here, tension 2. If I'm saying right now that tension 1 equals tension 2, that means this one gives you counterclockwise torque, this one gives you clockwise torque. If the tensions are the same, that means the torques are the same. Will this disk ever rotate? No, because if you have two forces or two torques in opposite direction, equal magnitude, the disk will never rotate. So that means if you have some kind of mass M1 and M2 over here, we can no longer say, let's say M2 is heavier, so it's going to slide down, right? It's going to start going down. We can never say that the tension are the same anymore. We could before. Why? Because we were saying the mass of the pulley is zero, so the pulley doesn't give us rotation. It's not rotating. In that case, the rope was just sliding, so the tension was the same, but no longer. So the rope passes over a pulley and connected to an object in linear motion. Now, the rope does not slip as the pulley rotates. Now the pulley is rotating, which means it's no longer massless. So it has a mass. Well, if it has a mass, it has a moment of inertia. If it has a moment of inertia and starts rotating, that means there is a net torque acting with this moment of inertia. It gives you angular acceleration. So that's why now we have to talk about that. That means there's a tangential velocity and acceleration of the rim of the pulley must match the motion of the object. So let's say this guy moving with some acceleration a. So let's say a1. Oh, so this is a2. This one has an a1. Now there's also an a3 acceleration of the linear acceleration of the disc or the pulley. Well, one thing stays the same is that they still have the same acceleration. That means acceleration of the pulley, object one and object two, still the same. Tension no longer the same, but at least acceleration, all of them are the same. And object, if I'm applying the velocity of the object to the pulley, then I can rewrite that in terms of omega times r. And acceleration of the object, then I times alpha. Alpha times r, which are the equation for the conversion from the linear to the rotational for the velocities and acceleration. And this is a motion constraint for a non-slipping rope. Okay. And all right, so then I'm going to give you an example in terms of how to use a problem now dealing with the pulley that is rotating. That means now you have to take the pulley into account. So, okay, so we wrap a light non-stretching cable around the solid cylinder with a mass M and a radius r. The cylinder rotates with a negligible friction about the stationary horizontal axis. We tie the free end of the cable to a block of mass M and release the block from rest at a distance h above the floor. As the block falls, the cable unwinds without stretching or slipping. So what we want to do is to find the speed of the falling block and angular speed of the cylinder as the block strikes the floor. All right, so that means we're going to be needing to find the linear speed of the object, falling object, and angular speed of the rotating cylinder. Okay. Now, this problem I can do two different ways. One of the ways I can do using rotational kinematics and dynamics, along with the linear kinematics dynamics. The other one we can use, energy method. Okay, because one thing we can say here is this: the energy is conserved because basically the gravity doing the work, right? And in terms of then object, so mechanical energy, right, is combination of kinetic plus potential. So when the object at some height h, then all the energy is potential energy because it's at rest, it's not moving. Same thing with the disk. There's no rotational kinetic energy. Then when you let go of the object goes and hits the floor, and all the potential energy is converted to the kinetic energy. That means I can then write this in terms of, I don't know, let's say point A and then point B. Then I can say energy at A is equals to energy at B. Ka plus Ua equals Kb plus Ub. I can basically write it like that. It can be very, simplified because we start from rest. Both the block and the pulley starts from rest. There is no kinetic energy at all. And then when it hits the ground, well, all the potential energy has been converted to kinetic energy. That means there is no potential energy at point B. So as you can see, right, this simplifies to then potential energy at point A, then completely converted to kinetic energy at point B. Okay. The only thing here is there are two types of kinetic energies. Okay, so, sorry. Potential energy is m times g times h, and h is the height of point A relative to point B. But for the kinetic energy, I have kinetic energy of mass 1. So let's say m is the falling object, v square. But I also have a pulley that has rotation. So it's 1/2 I omega square. Remember, that's a rotational kinetic energy. It means this is then K translational kinetic energy at B plus rotational kinetic energy at B. And I have, like, let's say one object that's moving, as a rotational, other one is a linear motion. Okay. That means this is my, equation. Okay. All right. Then from here, I can start, simplifying and also doing some um, substitutions. Remember, so V, as we talked about in the previous slide, object's velocity is related to the angular velocity of the pulley with r times omega. Okay, so that means this is equals to r times omega, which means that omega over there can be replaced with v over r. Also, moment of inertia, it's a disk, solid disk, so it's 1/2 m times r square. That means I can say, all right, so this mgh is equals to 1/2 mvb squared plus, this is also technically b, but right. So it's then 1/2 moment of inertia written as 1/2 mr squared. Then angular velocity written as v over r squared. Again, this is v at b. So that means from here you can see that I can completely cancel the r because it's r squared here and r squared over there, and have then mgh equals 1/2 mvb squared plus then 1/4 uh, m big M, right? VB squared. That means I'm saying that both pulley and the block have the same linear velocity, because they do. Because I'm talking about the rim of the disk. So then here I can factor out. I can say it's 1/2 m plus 1/2 m VB squared, like this, and then just basically solve for the VB. So then VB will be equals to, then rearrange and just basically solve for this, square root of 2gh over 1 plus m over 2m. So basically factor out, that this is what we get. That means this is basically the equation for the speed, right? Finding the speed. Well, we're not given any values for the mass m or the block or the pulley, so I can't really calculate any specific values. So this is basically mostly finding the expression. And this is what we get. And you can see, right, in a way what I have is, if the pulley was massless, and if I would have done this experiment, this example, I would have calculated V to be square root of 2gh, if you want to like go back and look at what we've done. And this is basically can be also looked from here. Then if the mass of the pulley was 0, then that term would have been 0, and you would have had just exactly square root of 2gh for the velocity of the block as it's going down. Okay. That means this is something that you can do. Right. Also pay attention that in the lecture notes I might have some extra problems for you to look at.